Welcome to The Explainer. So, today we're unraveling a pretty fascinating mystery that's quite literally hiding right beneath our feet. We're talking about the absolute foundation of modern civilization concrete. I mean, it builds our soaring skyscrapers, our massive dams, our endless highways. But here's the wild part despite being one of the absolute strongest materials on the planet, it almost always cracks. Today, we're diving into exactly why concrete cracks, even when it is mixed, poured, and finished absolutely perfectly. Let's get right into it. Think about the last time you were walking down the street and you noticed a jagged crack running right across the pavement. I want you to ask yourself, is that cracked sidewalk actually a mistake? Did someone just do a bad job? We naturally assume that a crack is a sign of failure or poor workmanship, or maybe even structural collapse. But there's this massive paradox between concrete's reputation as this indestructible, rigid monolith and the sheer reality that practically every single concrete structure you see has cracks in it. Well, the truth behind this paradox is probably going to completely change how you view the built environment. As our source material puts it, and this is a direct quote, concrete is a brittle material which develops microcracks even before any load is applied. Yeah, you heard that right. Cracking isn't always a sign of a mistake. It's actually an inherent fundamental property of concrete from the very beginning. Literally, before a single car ever drives over a brand new bridge, the concrete has already started to fracture. No way, right? So to really understand why this happens, we have to kind of step away from the visible everyday world and zoom way, way down into the microscopic chemical reactions that happen while concrete is curing. Because concrete isn't just, dried mud. It's actually a super complex chemical process called hydration. The cement and the water react to form this crystalline matrix that aggressively binds the sand and gravel together. And honestly, it's right here, within this microscopic chemistry, that our whole cracking story really begins. Inside this curing mix, there's a really critical area known as the transition zone. Basically, this is the interface between the solid aggregate, like your rocks and sand, and the hydrating cement paste itself. You can think of this zone as the weakest link in the entire chain. Here's why. Water in the mix naturally tends to pool around the aggregate, so this transition zone actually suffers from a much higher degree of shrinkage as the cement hardens. And as it shrinks, it pulls away from the rock, creating these microscopic stress fractures right at that boundary line. Now, if you take a look at the dark, jagged lines running through the paste and right around the aggregate borders here, this is literal, visual, scientific proof that these inherent microcracks exist long before a structure ever carries even an ounce of weight. It's just a naturally occurring network of tiny flaws, basically baked right into the chemistry of the material from day one. Okay, so if the chemistry sets up the weakness, it's the physical forces that pull the trigger. And the absolute biggest culprit behind all of this cracking? Volume change. From the very second concrete is poured, it starts undergoing massive internal shifts. It's essentially shrinking and expanding, changing its volume in a way that its brittle, hardened state just simply cannot accommodate without, tearing itself apart. And this volume change isn't just happening in one simple way. It's really more like an internal multi-front war. First off, you've got plastic shrinkage. That happens when the concrete is still wet and the water just evaporates way too quickly. Then you have drying shrinkage, which is more of a long-term process as moisture slowly escapes the hardened paste over time. Add to that autogeneous shrinkage, which is basically a minor volume loss due to the chemical reaction itself. And finally, thermal shrinkage. That one hits when the massive amount of heat generated by the curing cement finally dissipates, which causes the concrete to suddenly cool down and contract. To really grasp how incredibly sensitive this whole process is, just consider this specific limit: 1 kilogram per square meter per hour. If the evaporation rate on freshly poured concrete exceeds that number, which, by the way, easily happens on a hot summer day or if there's a dry wind, it reaches a critical state. Basically, water is leaving the surface faster than it can be replaced from below, so the surface simply collapses, and boom, you get rapid plastic shrinkage cracks before the concrete has even completely hardened. But what about long-term drying? Well, engineering codes, like the Indian Standard for Concrete Design, for example, actually mandate that engineers must assume a total shrinkage strain of approximately 0.0003. Now, I know that sounds like a tiny, almost insignificant decimal, but let's put that into perspective. Over a 10-meter slab, that actually equals 3 solid millimeters of physical contraction. By hard-coding this metric right into the design standards, the scientific community is openly acknowledging that shrinkage is not some rare accident. It is a calculated mathematical inevitability. Okay, so we've established the internal threats, right? The heat, the moisture loss, the volume changes that create those initial microscopic cracks. But here's the thing. This builds into a much, much larger problem. Because once the concrete's armor is breached by those microcracks, it essentially acts as an open doorway to a whole host of massive environmental threats. We're talking about external forces like freezing and thawing, alkali aggregate reactions, and chemical sulfate attacks. They can easily get inside those cracks and just absolutely wreak havoc. Actually, one of the most fascinating and definitely one of the most destructive of these external invaders is the alkali silica reaction, or ASR. This is literally an invisible chemical enemy. What happens is the alkalis in the cement react with the reactive silica in the rock aggregates to form this gel. But hold on, this isn't just any normal gel. It is an unlimited swelling gel. So as it absorbs moisture from the environment, it relentlessly grows. It expands inside the tiny voids and cracks, and it exerts this massive internal osmotic pressure that literally cracks the concrete wide open from the inside out. Now you can actually see how that microscopic ASR swelling manifests in the real world right here. Do you see this kind of webbing effect? That's what engineers call map cracking. The cracks form this really distinct pattern, almost like the borders on a map. And it's providing macroscopic evidence of that invisible gel expanding right under the surface. It's just relentlessly pushing the concrete apart in all directions simultaneously. And all of this brings us to a pretty devastating feedback loop. It's the cycle of environmental deterioration. It starts exactly like we discussed. Inherent internal shrinkage creates those initial tiny microcracks. Next, that opens the door for external water and chemicals to just infiltrate right in. Once they're inside, maybe the water freezes and expands by 9%, or maybe sulfates chemically attack the paste. Ultimately, all this internal pressure widens the cracks even further, which, you guessed it, only invites even more aggressive agents inside. It's just this progressive, never-ending cycle of destruction. So, with all this cracking and deterioration seemingly hardwired into the material itself, what's the resolution? I mean, if we know concrete actively wants to tear itself apart, how on earth do structural engineers actually design buildings that manage to last for decades or even centuries? Well, the answer lies in designing for durability, and it actually requires a completely counterintuitive approach to how we normally think about strength.
You'd probably naturally assume that the absolutely strongest possible concrete is the best, right? Well, actually, scratch that. It's not. High early strength concrete, which uses a ton of cement, generates very high thermal shrinkage simply because it gets so incredibly hot. It also has very low creep, which basically means it's super rigid and it cannot relax under stress. Because of that, it's actually highly prone to cracking. On the flip side, moderate or even low-strength concrete shrinks less, and it can subtly deform and relax to relieve that stress. This makes it much, much less likely to fracture. Pretty wild, right?
So the crucial takeaway here is that engineers aren't just blindly chasing pure unyielding strength. What they're really looking for is a property called extensibility. Now, extensibility is basically the ability of concrete to stretch and deform just a little bit without snapping. By using the exact rate mix to achieve a lower elastic modulus and a higher creep, along with, of course, perfectly placed steel reinforcement, engineers don't actually try to stop concrete from moving. Instead, they manage the movement. They literally manage the cracks.
It turns out building a durable world isn't really about forcing nature into submission. It's about working with the chemistry. As our source text beautifully concludes, and I love this quote, concrete should not be abused. It should be used with understanding, love, and care. Building with concrete requires an incredible amount of respect for its true physical and chemical nature, because it's only when we finally understand its weaknesses that we can engineer magnificent lasting strengths.
We've definitely covered a lot of ground today, all the way from the microscopic transition zone right up to the immense pressures of environmental deterioration. So, I want to leave you with this final thought. The next time you're out and you walk past a cracked sidewalk, are you going to see a mistake? Or are you going to see a fascinating, inevitable result of chemistry and physics? Thank you so much for joining me on this explainer. Keep looking at the world with curiosity, and I'll see you next time.